Thank you very much. Thanks everyone for joining in, and thanks Reach for having me. So I will spend the next 15 minutes or so telling you why lubricants are really important in our fight against climate change, and they look so ordinary, or we think of them as some really ordinary things, and we actually don't really think about them at all. But actually, there are complex engineering systems which have really great potential for reducing emissions and making automotive systems greener. So, okay, hold on here. So we already heard the talk from Karen, which was really nice, about one way of greening, of making automotive systems greener, and that is changing the way we fuel them, so that in order to reduce or make them carbon neutral. And I think that on top of this, we should also give a thought about what are the ways in which we can get our automotive systems to basically use less energy, so that we can do more with less fuel. And it's actually not only automotive systems, but all sorts of machinery which is powered, like industrial machinery, for example. So there is a really vast range of systems which can really be improved by thinking on how can we reduce the amount of energy they use. And not only the amount of energy, but the amount of material, really material sources. So let's take the example of a car, because we are familiar with it. So there is, for example, materials wear from the friction between the tire and the tarmac, or there is corrosion, which also means that materials is consumed and has to be replaced, and that comes to an energy and material cost. And then every single moving part within our car, within our automotive system, will have some friction to overcome, and overcoming friction costs energy. So I would like to kind of get you to think during this talk that we can think of all these problems as an additional things that's really important to think about when we think about making our automotive systems greener. Now, these three problems that I've talked about, which are just an example, they all come under the umbrella of tribology. So tribology is the science of the engineering discipline which studies friction and wear, and way to overcome friction and wear. So, for example, lubrication. And I would like to kind of digress for 1 minute and talk a little bit more about tribology, just because it's such an important engineering science. And generally, people who are not in engineering have actually never heard of it. So if in this moment you're sitting down and you're eating a snack, the contact between the food and your teeth, that is a tribological contact, because you're sort of moving your teeth against the food, and there will be like friction and wear acting there. Or, when I move my hand like this, the bone and the socket, that is a tribological contact, and the synovial fluid that is lubricating it is the lubricant. So there is a whole area of tribology which deals with the body, and that's also like creams and hair products. That's all biotribology. Then tribology can look at a really large scale, so tectonic plates moving against one another. That is a form of tribology. They call it geotribology. And it can look at a really, really tiny scale. So what I'm showing here is a microelectromechanical system. It's just a really, really tiny cogs that's actually really hard to make move, because there's such high surface energies, and they need really special lubricants. So tribology is not only the car, is not only lubricant in your car, but it's really a huge field, a huge discipline. And I will just talking about a really tiny element of it. And however, even just this tiny element is really important. So the reason why I think that all of us who do like this research in lubricant engineering think it's really worthwhile is because a large part of the world total energy consumption comes from tribological contacts. So there's various reports. These numbers I've taken here are from this report, but a quarter of the world energy consumption comes from overcoming friction and wear. So that is a really large amount. And the way we can overcome it is, designing better contacts, designing better materials, designing better lubricants, and by looking at what savings can be done with these novel designs. Transportation is actually one of the fields, of the areas where a lot of energy can be saved with this by taking action now and implementing novel technologies. So I strongly believe, I feel passionate about the fact that this is really an important way to tackle going carbon neutral. Right. So within this framework, I want to talk about lubrication science, because this is what I do. So as I said, so lubrication science is about lubricating a contact and reducing the friction. So this is an example of this is, let's say, two ball bearings or two surfaces in contact. So when they're in contact, and you can just try, with your hands, and you press them, and then you try to slide them. You have to apply quite a lot of force to move them. So this is having high friction. And now, if we take them and just rub an oil or a cream, and you do the same, then the hands would slide much more easily. And so why is it? How does a lubricant work, and what is a lubricant? So a lubricant is a liquid which has fairly high viscosity. So this is an alkane oil molecule. So this is a way how you can have high viscosity in the liquid, is having just a really long molecule. And basically what happens is that all these long molecules get tangled together a bit. If you ever try to take spaghetti out of a of a bowl, that's how it looks like. They're just tangled together. And so when you move them by pouring the liquid, for example, they first have to disentangle themselves, and so that they're able to move. Having something with high viscosity makes quite a good lubricant. Now, when we just add it to our contact, to our two surfaces, a little bit will go in the middle, a lot of it will go outside. So it will provide some separation already of the two surfaces. So we already go from something which is completely, really hard to move, to something which is a little bit easier to move. Then when we take our contact with the lubricant and then we move it, what happens is that the movement sucks all of the molecules inside the contact. And also with time, it kind of moves them and rotates them so that they're aligned. And you form a nice film which separates the surfaces. And so the way that reducing friction works is that when you're moving these two parts, these two components, all you're doing is having these long molecules sliding on top of one another, which is much easier in terms of the energy that you have to provide to the system, than having two solid blocks with a lot of asperities trying to slide on top of one another. So this is how a lubricant works. And okay, from what I say, it might sound that we have it all worked out, right? Like we know how a lubricant works. We know that we need a certain viscosity, but actually there are still a lot of challenges in lubrication science, and I will just talk about one. But I think it should kind of give you an idea of what we need to think about when we are trying to improve a lubricant and make it more efficient and in that way reducing the friction. So one example that I want to talk about is that of boundary lubrication. Maybe I'll start from here to explain boundary lubrication. So boundary lubrication is this case. So it's the case when your surfaces are not moving and you have the lubricant, and so there's not the formation yet of this nice thick film which you get when the surfaces are in movement. You have that the surfaces are still quite close together and there is a bit of lubricant in the middle. The same thing could also happen when the surfaces are moving, but there is really a lot of pressure pushing them together. But for now, let's think of these surfaces being static. And maybe the way one can try and imagine it is the moment that when you switch on your car. So when your car is switched off, you have this situation. All the components are static and there is the lubricant which somewhat separates them. And you have to go from this case to that case. And to do that, you have to build this film and overcome basically the friction that you have when you don't have a nice thick film of a lubricant. And to visualize it a little bit better, let's just think of an engineering component. So these are ball bearings in their casing. And if you look at them, they look like beautifully shiny, like mirrors. So one would think this surface is completely smooth. Actually, when we go and look really at the nanoscale, this surface is not smooth at all. It's really, it's got asperities. It's a rough surface. So the yellow thing is the lubricant, and there's the gray is the two surfaces in contact. So when we have the surfaces are not moving, and we have just a very thin film of a lubricant, a lot of the asperities will be in contact. And so what happens to go from the static to the moving scenario with a nice thick film is two things. First of all, there will be a lot of energy spent to overcome this friction of this asperity moving. And secondly, this asperity will get damaged. So we will also have wear, which will then produce debris. The debris will remain in the system, and overall, it will end up damaging the system. So boundary lubrication is really a big problem and is really a big energy expenditure in all machinery with moving parts. It's really the startup when you turn on the engine. So the way to do it is to try and find a way then to never have this scenario, never have the asperities in contact. So and so this is something I have worked on. And so the way to do it is to have additives, to add additives into the oil. So in this case, there will be friction modifying additives, they're called. So if you remember from a few slides before, the oil, it looks like this. It's these long carbon molecules with hydrogens. And the additive looks very, very similar, except it has a little different head, which is polar. So the polar head is here. So what I have here is a description of a contact. So this on the top at the bottom are the surfaces of steel. And then here in white and red are the polar heads, which are these ones, which are attached to this still surface. And these little vertical spaghetti here are the non-polar tails. So what happens is that basically this molecule will really compactly get stuck onto the surface and form two little bristles, which make sure that the surfaces are always separate. And as you see, the tails are the same as the base oil. So there are no problem really with the interaction between the tail and the base oil, because they're basically the same thing. And then when this thing starts to slide, the film will build up eventually. But even at the very beginning of sliding, this oil that will not have to will not have to kind of compete with the asperities. It will sort of, the tails will just do the job basically of the oil in keeping the asperities separate. So this is how we design modern oil, is by trying to understand what are the problems to overcome, and finding an engineering solution or a chemical solution to this problem. And other problems that could occur are, for example, in hybrid cars, which have also an electric engines, there will be a lot of copper parts which easily corrode. So in that case, what we want to do is to make sure that there's ways to protect all these surfaces from corrosion. And so there will be a different additive which will do that. Or there are certain materials which will wear very easily, and so there will have to be anti-wear agents. So in the end, what one ends up with is a really complex and customizable multi-component system, where we have some components that will attach to the surface, either to protect the surface, for example, the corrosion inhibitors, or the anti-wear agents, or these friction modifiers. They're not to protect the surface, but they're to keep the surface separate. Or there will be viscosity modifiers, which, for example, might kick in at a certain temperature when the viscosity of the base oil becomes too little. Or there will be more technical components, I suppose, like anti-foam agents, for example. And sort of the whole idea of lubrication science is to tune this zoo of inhibitors in a way that improves the performance. And this comes then with its own challenges. So, for example, the friction modifier that I showed you just now, so with the polar head and the long tail, is actually an acid which will eventually corrode the surface. So although it really helps at startup, then it has other effects down the line. So a lot of research that what we are doing is that, okay, can we find something that works as good as a friction modifier without, in, I don't know, 5 years' time, completely destroying the engine or wherever it is put. Or there's, for example, the most common and the most useful anti-wear agent was actually highly toxic, and so it had to be removed at some point from the market. But nobody has found anything which works quite as well. So there is really always a work in progress in introducing new components and understand what they do to the system. So it is a really always a work in progress, and hopefully we are sort of slowly tuning the chemistry to find the best possible results. Okay, so with this, I would like to conclude. So I showed you one example of how we try to build better lubricants to produce better tribology for automotive system to eventually lead us to energy savings and a carbon neutral world. What I showed you is improved formulation of lubricant and lubricant additives. And but as I said, this is just one aspect of tribology, and there are a lot more, like different like greases or different surface coatings that are also becoming more and more relevant. So I hope that you found this interesting and you will look with renewed interest at your car lubricant. And I would like to thank you all for your attention.